When you look at a map of the globe, the southern pole is always depicted as a monolithic white void. For generations, the human mind has processed Antarctica as exactly that, a static, silent, and dead expanse of ice at the bottom of the world. A frozen wasteland completely locked in time, passively waiting out the eons. But radar topography, satellite gravimetry, and deep ice core drilling have completely shattered this illusion. The truth is far more complex. The endless white surface is nothing more than a geological lid, a crushing blanket of ice miles thick, hiding one of the most violently active landmasses on the planet. Beneath the crushing pressure of trillions of tons of ice, there is a living, breathing continent. It holds massive mountain ranges that easily rival the European Alps, yet they remain entirely unseen by human eyes. It hides an intricate continent-wide circulatory system of high-pressure subglacial rivers and massive liquid lakes that have been sealed off from the atmosphere for millions of years. Even more surprising, the bedrock of this frozen world is scarred by a massive, active volcanic rift system that continuously pumps geothermal heat directly into the underbelly of the ice sheet. Antarctica is not a passive freezer. It is a highly dynamic geological engine. The mechanisms operating in total darkness down there dictate global ocean currents, control planetary sea levels, and provide our absolute best earthly blueprint for how biological life might survive on the frozen moons of Jupiter and Saturn. The frozen continent is holding the master keys to both our planetary future and the broader mysteries of extreme astrobiology. Today, we will explore the topic of Antarctica, secrets beneath the frozen continent. Before we descend into the hidden depths of the seventh continent, please take a second to like this video and subscribe to the channel. Also, leave a comment below letting us know exactly where in the world you are and what time it is as you watch this journey unfold. To truly understand the massive forces at play, we must first tear away the ice. When researchers process the latest radar topography data, stripping the continent of its frozen shield, a stunning physical reality emerges. Antarctica is not a single, unified landmass. It is a continent suffering from a severe geological split personality. The blinding white surface gives the illusion of homogeneity, but the bedrock beneath tells a story of two entirely different worlds, divided violently by the sheer wall of the Transantarctic Mountains. On one side lies East Antarctica. This is a massive, ancient, and incredibly stable continental block, known to geologists as a craton. The crust here is exceptionally thick, extending deep into the mantle of the Earth like the heavy keel of an ocean liner. The bedrock of East Antarctica is mostly situated well above sea level. If you were to somehow vaporize all the ice covering it today, you would be left with a vast, high-altitude landmass, roughly resembling the physical footprint of modern Australia. Its geological foundations were forged billions of years ago during the volatile assembly of the earliest supercontinents of our planet. East Antarctica acts as the planetary anchor at the bottom of the world. It is a silent repository of deep geological time where the deep rocks have remained largely undisturbed by tectonic tearing or volcanic violence for eons. But across the mountain divide, the story drastically changes. West Antarctica is an entirely different beast. For decades, scientists assumed it was simply a smaller, contiguous extension of the Eastern Bloc. However, advanced gravimetric satellite data, which measures minute changes in the gravitational pull of the Earth to map underground density, combined with deeply penetrating radar, has mapped a submerged truth. West Antarctica is not a solid continent at all. It is, in fact, an archipelago. It is a fractured, tectonically active collection of smaller landmasses, scattered islands, and incredibly deep subglacial basins. The reason it appears as a solid continent on modern maps is due to a fascinating planetary mechanic known as isostatic depression. The ice sheet covering West Antarctica is so unimaginably heavy, reaching thousands of meters thick in several regions, that its sheer gravitational mass has physically crushed the bedrock beneath it. The crust of the Earth is not a perfectly rigid shell. Over long geological timescales, it behaves more like an elastic membrane resting on the viscous fluid of the mantle. The astronomical weight of the ice has pushed the continental crust of West Antarctica deep into the planet. Today, vast sections of the West Antarctic bedrock lie thousands of meters below sea level. This leads to a profound realization. If the ice were removed tomorrow, ocean water would immediately rush in to fill the topographical voids, completely submerging the interior. West Antarctica would instantly become a freezing inland sea, dotted with island chains, rather than a contiguous terrestrial landmass. But the problem does not stop there. This specific geological architecture creates an inherent existential vulnerability for the modern climate. Because the bedrock of West Antarctica sits so far below sea level, the ice sheet resting on top of it is classified as a marine-based ice sheet. This means the ice is not simply sitting on dry, elevated land. Its outer edges are in direct, continuous contact with the deep ocean. The seawater can flow beneath the ice, interacting directly with the grounding line, which is the exact point where the ice physically meets the rock. This structural reality makes West Antarctica acutely sensitive to even microscopic shifts in deep ocean temperatures. At a planetary scale, the implications of this topography shift completely. We are looking at a system where the solid Earth and the fluid ocean are locked in a high-stakes mechanical balancing act. The deep, bowl-like basins of West Antarctica represent a topographic trap. As long as the ice holds the perimeter, the system is mostly stable. But if the ice recedes beyond a certain geographical threshold, there is no elevated barrier, no high ground to stop the collapse. The ocean water simply flows further downhill into the deep basins, eating the ice from below in an unstoppable physical feedback loop. And right here, this geological mechanic begins to connect to a much larger question about planetary evolution. The interaction between massive surface loads, like planetary ice sheets and rocky crusts, is not unique to Earth. It is a fundamental mechanism of geophysics that governs the evolution of any active, layered world. When astrobiologists and planetary scientists look at the icy moons of the outer solar system, such as Europa or Enceladus, they are forced to consider these exact same dynamics. The way a crust flexes, fractures, and depresses under the weight of an icy outer shell determines how heat escapes from the core, whether subsurface oceans can remain pressurized and liquid, and ultimately, whether the planetary conditions can sustain the chemical reactions necessary for biology. On Earth, the immense weight of the Antarctic ice has fundamentally altered the shape of our sphere. If that weight is eventually lost, the crust will not simply stay down. It will undergo isostatic rebound. Over thousands of years, the bedrock of West Antarctica would slowly rise back up, lifting out of the mantle in a delayed, slow-motion geological bounce. This process would displace ocean water globally, redistributing mass across the surface of the planet and subtly altering the rotational axis and gravitational field of the Earth. The ice may seem transient, but its physical grip on the solid crust dictates the geological future of the entire globe. Understanding this hidden depressed topography is the crucial first step in decoding the true scale of the forces operating in the dark at the bottom of the world. Deep within the heart of the stable eastern sector lies one of the most baffling geological anomalies on our planet. Suspended in eternal darkness, buried beneath nearly 3 kilometers of solid ice, is a colossal mountain range known as the Gamburtsev Subglacial Mountains. Discovered by Soviet seismologists in the mid-20th century, this hidden topography rivals the European Alps in both scale and majesty. The peaks rise up to 3,000 meters above the valley floors, and the entire system stretches across a distance of 1,200 kilometers. Yet, no human being has ever seen a single stone of this massive formation. The Gamburtsev range is a ghost trapped in the ice, and its very existence challenges the foundational laws of planetary geology. In classical geophysics, massive mountain building is a violent process dictated by the rules of plate tectonics. High, jagged ranges are almost exclusively the result of massive tectonic collisions at the active margins of continental plates, where land masses smash together and crumple upward. The Himalayas, for instance, are currently being thrust into the sky by the ongoing collision between the Indian and Eurasian plates. But the Gamburtsevs completely ignore this rule, nor they are located dead center in the middle of the East Antarctic Craton. A craton is the oldest, thickest, and most rigid core of a continental plate. It is geologically dead, a stable shield that has not experienced significant tectonic deformation for over 500 million years. According to every standard model of planetary evolution, the center of an ancient craton should be a flat, highly eroded plain. Finding a massive, jagged mountain range here is like finding a raging volcano at the bottom of a serene, undisturbed swimming pool. This spatial paradox introduces a severe chronological contradiction. High elevation combined with sharp, jagged peaks is the universal signature of a young mountain range. Gravity, wind, and water are relentless equalizers. Over hundreds of millions of years, the forces of erosion will grind any towering peak down to a soft, rolling hill. If the bedrock of East Antarctica is over 1 billion years old, these mountains should have been erased from the map eons ago. Conversely, if the sharp peaks indicate that the mountains are young, there must be a recent, massive tectonic engine driving them upward. Yet, seismic readings confirm that the crust below the Gamburtsevs is thick, cold, and entirely devoid of recent tectonic activity. To resolve this impossible contradiction, geophysicists had to develop an entirely new model of tectonic resurrection. Modern data suggests the Gamburtsevs were not created in a single event, but through a complex, multi-stage geological process spanning 1 billion years. The origin story begins with ancient continental collisions that formed a massive, dense root of rock deep within the crust. Hundreds of millions of years later, when supercontinents began to tear apart, a massive rift system developed near this ancient root, similar to the modern East African Rift. This rifting process injected tremendous thermal energy from the deeper mantle into the cold lithosphere. The extreme heat caused the deep, dense root to expand, become buoyant, and dome upward. Later, shifts in tectonic stress compressed this heated crust, squeezing the rock and violently thrusting the mountains toward the sky. They are ancient mountains that were given a sudden, artificial youth by deep mantle heating. But the problem does not stop there. This mechanism explains how the mountains rose, but it completely fails to explain how they survived. Even with a tectonic rebirth, the relentless forces of erosion should have destroyed these peaks long before modern humans evolved. This leads to a deeper, more profound realization about the interplay between climate and geology. The savior of the Gamburtsev Mountains was a sudden and catastrophic shift in the global climate system. Roughly 34 million years ago, as global temperatures plummeted, the Antarctic ice sheet began to form. Initially, slow-moving glaciers carve deep valleys into the rock, sharpening the peaks. But as the climate continued to cool, the ice thickened to an unimaginable scale. Deep within the interior of the continent, the temperature dropped so radically that the base of the ice sheet completely froze to the bedrock. At this precise moment, the mechanical grinding of the glaciers stopped entirely. The ice ceased to be an agent of erosion and transformed into a flawless, impenetrable cryogenic shield. It locked the topography in a state of suspended animation. The Gamburtsev mountains are not just hidden by the ice, they are preserved by it. They are a perfectly intact geological fossil from a time before the Earth froze over. At a planetary scale, the meaning of this changes completely. This mechanism of cryogenic shielding offers a radical new lens through which we must view other worlds in our solar system and beyond. When we look at the frozen crust of Mars, or the deep ice shells covering the ocean moons of the outer solar system, we are not just looking at weather, we are looking at planetary memory banks. The realization that extreme ice can entirely shut down mechanical erosion implies that the deep past of a dead or dormant world might be perfectly preserved right beneath its frozen surface. If we want to understand the ancient tectonic history of terrestrial planets, or decode the geological mechanisms that might support deep biosphere habitats on alien worlds, we must first master the physics of the ultimate planetary preservative. The ghost mountains of Antarctica prove that sometimes the only way a planet can remember its violent past is by freezing it alive. How do you map a continent you can never physically see? For most of human history, our understanding of geography relied on the electromagnetic spectrum of visible light. We looked at the surface, and our eyes processed the reflected photons. But in Antarctica, visible light is completely useless. The ice sheet acts as a flawless blinding mirror, reflecting the sun and hiding everything beneath. To map the true face of the seventh continent, geophysicists had to completely abandon human perception and rely on the invisible physics of radio waves and planetary gravity. They had to build proxy sensors to feel the shape of a buried world. The primary tool in this endeavor is ice-penetrating radar, also known as radio echo sounding. The mechanism relies on a highly specific physical quirk of frozen water. While liquid water is highly conductive and absorbs radio waves, solid, cold ice acts as a dielectric medium to certain frequencies of electromagnetic radiation. A glacier that is 3 kilometers thick is essentially as transparent as a pane of clear glass. For decades, fleets of heavily modified aircraft have flown endless, perilous grid patterns across the continent, firing low-frequency radio pulses straight down into the ice. When these radio waves travel through the frozen matrix, they move at a known, constant speed. The moment they hit a material with a radically different density and electrical property, like solid bedrock or a subglacial lake, a portion of the signal reflects back to the surface. By precisely measuring the time of flight of these returning echoes, scientists can calculate the exact thickness of the ice and the topography of the rock below. It is similar to a bat using echolocation, but operating at a geological scale, bouncing signals off mountain ranges buried in eternal darkness. But the problem does not stop there. Ice-penetrating radar is a miraculous technology, but it has a fatal physical limitation. It only works perfectly when the ice is deeply frozen and resting on solid rock. The moment the radar signal encounters liquid water, the physics abruptly change. Saline seawater and highly pressurized subglacial meltwater scatter and absorb the radio waves, turning the data into impenetrable static. This creates a massive, critical blind spot exactly where the ice meets the ocean. The deep subglacial canyons of the coastline, where the most dangerous melting occurs, remain completely invisible to radar. To pierce these blind spots, scientists had to look beyond the ice entirely and measure the fundamental fabric of space-time. They turned to satellite gravimetry. Projects like the Gravity Recovery and Climate Experiment utilize twin satellites orbiting the Earth in tandem, separated by a couple of 100 kilometers. These machines do not take photographs. Instead, they constantly measure the microscopic distance between each other using precise microwave lasers. The mechanism here is purely gravitational. Everything with mass exerts a gravitational pull, and denser materials exert a stronger pull. A solid mountain of dense basaltic rock has significantly more mass than a deep canyon filled with less dense seawater or glacial ice. As the lead satellite flies over a buried mountain range in Antarctica, the slight increase in regional gravity pulls it forward just a fraction of a millimeter. The trailing satellite records this minute acceleration. By mapping these microscopic gravitational anomalies across the entire continent, supercomputers can reverse engineer the density of the material hidden below the surface. They are effectively feeling the invisible skeleton of the planet by measuring its localized weight. By combining the high-resolution spatial data from radar with the deep mass distribution data from gravity satellites, glaciologists created a master map known as Bed Machine. For the first time in planetary history, we have a continuous, high-fidelity model of the Antarctic bedrock. We can see the deep troughs that channel warm ocean water into the heart of the continent, and we can identify the exact ridges of rock that act as the final structural supports holding the great ice sheets in place. At a planetary scale, the meaning of this technological triumph changes completely. This framework of penetrating radar and microgravity mapping does not just tell us about the hidden past of Earth. It is the exact sensory blueprint required for humanity to explore the wider cosmos. When planetary scientists look at the solar system, they face the exact same physical barriers. The southern polar ice cap of Mars, the deeply fractured ice shell of Europa, and the geyser-spewing surface of Enceladus are all hiding immense subsurface environments. We are currently using the exact same radar technology developed in the skies of Antarctica to discover liquid water lakes beneath the Martian poles. We use the exact same gravitational anomaly mechanics to prove that a massive global ocean sloshes beneath the icy crust of Enceladus. If this methodology is correct, it does not merely map the topography of our own world. It provides the fundamental diagnostic tools for the field of astrobiology. The techniques we use to blindly feel the mountains of Antarctica are the very same tools we will use to hunt for the chemical signatures of extraterrestrial life in the dark, pressurized oceans of the outer solar system. Antarctica is not just a geographical puzzle. It is the ultimate training ground for decoding the hidden architecture of alien worlds. When the first fleets of radar-equipped aircraft began painting the hidden bedrock of Antarctica, they expected to find a continuous landscape of solid stone and frozen valleys. Instead, the incoming data revealed a profound anomaly. Deep beneath the eastern interior, the radar signals bounced off massive, perfectly flat surfaces. In the chaotic, jagged world of geological topography, perfect flatness implies only one thing. It is the signature of standing liquid. The radar had not hit rock, it had hit water. Researchers had unwittingly discovered a vast, interconnected network of subglacial lakes, the largest of which is Lake Vostok. Roughly the size of Lake Ontario, Vostok lies buried beneath nearly 4 kilometers of solid ice. The existence of a massive body of liquid water in the coldest environment on Earth presents an immediate thermodynamic paradox. surface temperatures in this region of the continent routinely plummet to -80 degrees Celsius. The ice sheet is an ancient, frozen monolith. Yet, at the very bottom, in total, suffocating darkness, millions of cubic kilometers of water flow freely. To understand how this is possible, we must look at the immense physical forces converging at the absolute bottom of the world. The mechanism keeping Lake Vostok liquid is a delicate balance of deep planetary heat and catastrophic overhead weight. The first factor is geothermal flux. The Earth is essentially a giant heat engine, fueled by the slow decay of radioactive isotopes in the mantle. This geothermal energy constantly radiates upward through the bedrock. In most places on Earth, this heat dissipates harmlessly into the atmosphere, but in Antarctica, the heat is trapped. The 3 to 4 kilometer thick ice sheet acts as an ultimate thermal blanket, a flawless insulator that prevents the planetary heat from escaping. The geothermal energy pools at the interface between the rock and the ice, slowly warming the deepest layers. But geothermal heat alone is not nearly enough to melt a glacier of this magnitude. The second, and more crucial, physical mechanism is hydrostatic pressure. When we consider the sheer mass of the ice sheet above Lake Vostok, the numbers become staggering. The weight of 4 vertical kilometers of solid ice exerts a crushing pressure on the base, hundreds of times greater than the atmospheric pressure at sea level. This extreme pressure fundamentally alters the thermodynamic properties of water. Unlike almost every other substance in the universe, water expands when it freezes because its molecules must arrange themselves into a spacious, crystalline lattice. However, the crushing weight of the Antarctic ice physically prevents this expansion. The pressure simply does not allow the water molecules to push outward and form ice crystals. As a result, the freezing point of water drops below zero. Under the tremendous weight of the East Antarctic ice sheet, water can remain perfectly liquid, even when its temperature registers several degrees below the normal freezing point. It exists in a state of supercooled liquid, held in structural limbo by the sheer gravitational force of the ice above. But the physics of this system reveal an even deeper complexity. Lake Vostok is not a stagnant dead pool of water. It is an active, dynamic hydrological engine operating in the dark. The uneven distribution of geothermal heat from the bedrock creates thermal convection currents within the lake. Water warmed by the Earth rises, while colder water near the ice ceiling sinks. This continuous circulation prevents the lake from freezing solid over deep geological time. Furthermore, the lake interacts continuously with the glacier above it. In certain regions of the lake, water slowly freezes onto the bottom of the ice sheet, creating what glaciologists call accretion ice. As the massive glacier slowly grinds forward toward the ocean, it carries this frozen lake water with it, effectively dragging pieces of the ancient lake out of the continent over tens of thousands of years. This mechanism of accretion ice presents a massive challenge for modern science. Drilling directly into Lake Vostok risks catastrophic contamination. If the highly pressurized water is suddenly exposed to a surface borehole, it could violently depressurize, or worse, toxic drilling fluids could poison a pristine environment that has been sealed off from the atmosphere for up to 25 million years. Therefore, scientists study the accretion ice trapped higher up in the glacier to understand the chemical makeup of the lake below, reading the frozen echoes of the water without ever touching the source. At a planetary scale, the meaning of this extreme hydrology shifts completely. The physics of Lake Vostok provide the most robust proof of concept for the survival of liquid oceans on alien worlds. When astrobiologists analyze the icy moons of Jupiter and Saturn, like Europa and Enceladus, They are looking at planetary bodies that operate on the exact same thermodynamic principles. These moons possess outer shells of solid ice kilometers thick, combined with massive internal pressures and internal heat generated by the gravitational tidal friction of their host planets. The subglacial lakes of Antarctica prove that solar radiation is entirely unnecessary for maintaining massive, liquid environments. If crushing pressure and deep planetary heat can keep Lake Vostok entirely liquid beneath an ancient ice sheet on Earth, the exact same mechanics guarantee the existence of dark, pressurized oceans across the cosmos. Antarctica ceases to be just a frozen desert. It transforms into an accessible, working prototype of the most common class of habitable environments in the universe. For a long time, the discovery of extreme subglacial environments like Lake Vostok left scientists with a comforting assumption. They believed these deep aquatic vaults were geologically quarantined, completely sealed off from one another by impenetrable ridges of bedrock, acting as stagnant time capsules of the ancient Earth. But as satellite technology evolved, specifically the use of precision laser altimetry, capable of measuring microscopic fluctuations in the elevation of the ice surface, a completely different reality emerged. The ice sheet was literally breathing. Scientists observed massive sectors of the continent's surface slowly deflating over several months, while regions hundreds of kilometers away simultaneously rose. This physical displacement revealed an astonishing physical mechanism. The subglacial lakes are not isolated at all. They are highly active nodes in a vast, interconnected circulatory system of high-pressure subglacial rivers. Antarctica possesses a continent-wide hydrology operating entirely in the dark. The physics governing this hidden river network are fundamentally completely different from the hydrology we experience on the surface of the Earth. On the surface, water obeys the simple dictate of gravity, flowing inevitably downward towards sea level, cutting valleys through the path of least resistance. But beneath the Antarctic ice sheet, the sheer mechanical pressure of the frozen canopy overrides gravity entirely. The weight of the ice creates massive gradients of hydraulic potential. Because the ice varies wildly in thickness across the continent, the pressure exerted on the water below is deeply uneven. This immense differential pressure forcefully squeezes the subglacial water across the bedrock, actively pushing it up and over submerged mountain ranges. In this high-pressure environment, water routinely flows violently uphill. It forces the liquid through narrow hidden canyons at tremendous speeds, carving deep channels into solid rock without any atmospheric weathering. We are looking at a pressurized plumbing system on a planetary scale, constantly redistributing massive volumes of liquid across the continental interior. But the implications of this flowing water do not stop at mere geographical curiosity. This deep circulatory system triggers a profound mechanical consequence that dictates the physical stability of the entire continent. When a highly pressurized layer of liquid water is injected directly between the solid continental bedrock and millions of tons of moving ice, it acts as a phenomenal hydraulic lubricant. In the rigid interior of the continent, where the ice is frozen completely to the rock, the glacier can only move through internal plastic deformation, creeping forward at a microscopic pace of a few centimeters a year. However, where the subglacial rivers flow, the rock-on-ice friction is suddenly reduced to near zero. This mechanism, known to geophysicists as basal sliding, fundamentally transforms the structural dynamics of the entire ice sheet. The solid foundation is replaced by a sheet of liquid ball bearings. This intense lubrication generates massive, fast-flowing arteries within the larger frozen matrix, known as ice streams. While they only account for about 10% of the volume of the continent, these highly lubricated corridors are responsible for discharging nearly 90% of the total ice mass into the surrounding oceans. They are the high-speed conveyor belts of the continent, and right here, this geological mechanic begins to connect to a much larger question about planetary climate survival. The speed at which Antarctica loses mass to the ocean is not primarily driven by the ambient air temperature slowly melting the surface. It is aggressively governed by the hidden fluid dynamics operating at the bedrock. If geothermal activity or warming ocean waters penetrating the outer edges inject more liquid water into this subglacial network, the lubrication drastically increases. The ice streams accelerate, pulling vast sections of the interior ice out into the sea at terrifying velocities. It fundamentally shifts our understanding of climate modeling. Supercomputers cannot simply calculate surface melt. They must attempt to simulate a hidden, high-pressure, chaotic fluid system that is constantly rewriting its own channels in the dark. The stability of global sea levels is entirely dependent on the friction maintained at the bottom of these frozen rivers. At a planetary scale, the meaning of this extreme fluid dynamic shifts completely. The interaction between internal plumbing and surface fracturing is not unique to Earth. It provides the exact mechanical blueprint for understanding the chaotic surfaces of icy bodies across the solar system. When we look at the deeply scarred and continuously shifting ice crust of Europa, a moon of Jupiter, we are observing a world governed by the exact same physical laws of basal lubrication. The subglacial rivers of Antarctica teach us how an icy planetary shell physically detaches from its rocky core, allowing massive tectonic plates of ice to slide, fracture, and resurface the globe. Furthermore, if biological material exists in the deep, warm oceans of these alien moons, it is precisely this pressurized network of flowing water that would transport organic nutrients from the dark interior up toward the icy crust. The hidden rivers of Antarctica are not just a local terrestrial anomaly, they are the universal transmission fluid of active, frozen worlds. By mapping how water destroys friction under our own ice sheet, we are simultaneously deciphering the massive geological engines of the outer solar system. Emerging from the deep interior and moving toward the coastline, the frozen landscape drastically transforms into the McMurdo dry valleys. This is one of the most extreme deserts on the planet, a region completely devoid of snow and ice cover, where the raw, ancient bedrock is violently exposed to the freezing winds. At the terminus of the Thwaites Glacier, which spills down into this barren valley, a shocking visual anomaly fractures the stark white and brown landscape. Flowing directly out of a fissure in the snout of the glacier is a brilliant, blood-red waterfall spreading across the frozen surface of Lake Bonny. When early explorers first encountered this striking phenomenon over a century ago, they logically assumed the vibrant color was the result of red algae blooming within the ice. But modern biogeochemistry has revealed a truth far more complex and geologically profound. The glacier is not bleeding organic matter, it is bleeding an ancient, heavy metal brine. The striking crimson color of blood falls is the result of a rapid, massive chemical reaction occurring at the exact boundary where the deep earth meets the atmosphere. The water discharging from the glacier is heavily loaded with dissolved ferrous iron. Deep underground, in the total absence of atmospheric oxygen, this iron remains in a colorless, soluble state. However, the moment this pressurized subglacial fluid breaches the surface and comes into contact with the oxygen-rich air, a violent oxidation event takes place. The ferrous iron rapidly binds with oxygen molecules, transforming into insoluble ferric iron oxide. The water, is literally rusting as it falls. But this chemical reaction is merely the surface expression of a much deeper planetary anomaly. The true mystery lies in how liquid water is flowing through a glacier in a region where the average annual surface temperature hovers around -20 degrees Celsius. To find the source of this liquid rust, radar scanning technologies had to trace the plumbing system back through the solid ice. They discovered that the source is not surface melt water, but an isolated subglacial pool of hypersaline water located several kilometers inland, trapped beneath a quarter-mile of solid ice. This subterranean lake was sealed off from the atmosphere approximately 2 million years ago, when a shifting climate caused the Thwaites Glacier to advance over a prehistoric fjord. As the seawater was trapped and isolated, the crushing cold of the encroaching ice began to freeze the top layers of the water. This leads to a fascinating mechanic of fluid physics known as cryoconcentration. When salt water freezes, the rigid crystalline lattice of the ice physically ejects the dissolved salt molecules. This pure ice forms at the top, while the expelled salt is driven downward into the remaining liquid pool. Over 1 million years, this continuous freezing process concentrated the salt in the subglacial lake to levels roughly 3 times saltier than the modern ocean. Because highly concentrated brine has a drastically lower freezing point than fresh water, this heavy, salty liquid can remain perfectly fluid even at significantly sub-zero temperatures. But the fluid dynamics at play here are even more bizarre. When this super cold brine finally begins to slowly freeze within the cracks of the glacier, it releases a microscopic amount of latent heat. This thermal energy, paradoxically generated by the act of freezing itself, is just enough to melt the surrounding fresh glacial ice. The heavy brine effectively melts its own escape tunnel through the solid glacier, acting as a slow-motion thermal drill, cutting upward through the ice over thousands of years until it violently breaches the surface. At a planetary scale, the meaning of this extreme system changes completely. Blood Falls is not a sterile chemical curiosity. When researchers sampled the red brine, they discovered a thriving, self-sustaining microbial ecosystem that has survived in total darkness and complete isolation for over 1 million years. Cut off from the energy of the sun and the oxygen of the atmosphere, these ancient bacteria have fundamentally rewritten their own metabolic rules. They survive by stripping electrons from the sulfur compounds and iron minerals scraped from the bedrock, effectively breathing rust and eating stone. And right here, this extreme biological mechanism begins to connect to the greatest questions in modern astrobiology. Blood Falls is the closest terrestrial analogue we possess to the subsurface environments of the planet Mars. Mars is a red world, heavily coated in iron oxide, possessing a frozen surface, but harboring deep, hypersaline aquifers mapped by orbital radar. If a complex microbial community can survive for millions of years trapped beneath the Thwaites Glacier by relying on chemical energy and iron oxidation, it profoundly expands our definition of the habitable zone. It suggests that a planetary surface, freezing solid, is not necessarily a death sentence for biological life, but merely a barrier that forces evolution deep underground. When we eventually drill into the Martian permafrost, or send submersibles into the deep oceans of the outer solar system, the biochemical blueprints we use to hunt for alien microbes will be directly based on the surviving inhabitants of this bleeding glacier at the bottom of the Earth. For the entirety of human history, biological science was anchored to a single, undisputed dogma: the sun is the absolute engine of life. The vast interconnected web of the terrestrial biosphere fundamentally relies on photosynthesis, the process by which plants and algae harvest incoming solar radiation to to convert carbon dioxide into organic matter. Without photons raining down from the sky, the planetary food chain collapses. When researchers first pierced the ice above subglacial lakes, like Lake Whillans and Lake Mercer, environments buried under a kilometre of solid ice, and plunged into absolute, eternal darkness, they expected to find a sterile abyss. Instead, the extracted water samples were teeming with a complex, thriving network of microorganisms. The discovery shattered the biological paradigm. It forced science to confront a profound question. How do you build an entire ecosystem in an environment where the sun never rises? The answer lies in a radical alternative to photosynthesis known as chemosynthesis. Cut off from solar energy, these microscopic life forms have fundamentally re-engineered their metabolic pathways to extract power directly from the solid Earth. Instead of capturing light, they break the chemical bonds of inorganic minerals. Deep in the subglacial waters, specialized bacteria hunt for dissolved compounds of iron, sulfur, and nitrogen. By driving chemical reactions that oxidize these raw elements, the microbes release microscopic bursts of energy. They use this biochemical electricity to pull dissolved carbon dioxide out of the dark water and weave it into the complex organic molecules necessary to build their cellular walls and reproduce. They are literally pulling life out of cold stone, but the existence of this mechanism introduces a massive logistical problem. A closed ecosystem cannot survive if its primary fuel source is finite. If these bacteria are constantly eating the available minerals in the water, those elements should have been completely depleted millions of years ago, starving the entire subglacial biosphere. To understand how this dark ecosystem sustains itself across deep geological time, we must look at the immense mechanical violence happening right above it. The overriding ice sheet is not merely a static roof. It is a highly active planetary-scale grinding machine. As millions of tons of solid ice slowly drag across the continental bedrock, the tremendous friction pulverizes the ancient crust. This relentless mechanical milling crushes solid rock into an ultrafine powder known as glacial flour. This continuous physical destruction exposes fresh, unweathered mineral surfaces, constantly bleeding highly reactive iron and sulfur directly into the subglacial river networks. The moving glacier itself acts as the mechanical digestive system for the biosphere below, continuously chewing the bedrock to feed the dark ocean. However, survival in this extreme environment requires a severe biological compromise. Chemosynthesis in near-freezing water is an incredibly inefficient process compared to the vibrant energy yields of solar photosynthesis. Because the energy margins are microscopically thin, the organisms living beneath Antarctica are forced to operate in a state of extreme metabolic conservation. These biological networks do not thrive in the way a rainforest thrives. They endure. Their metabolic clocks are stretched to the absolute limits of biological possibility. While surface bacteria might reproduce and divide in a matter of hours, these subglacial microbes might take decades or even centuries to complete a single cellular division. They exist in a haunting twilight state between active life and suspended animation, perfectly calibrated to outlast the slow ticking of geological epochs. At a planetary scale, the meaning of this biological resilience changes completely. The chemosynthetic networks of Antarctica force us to completely redraw the boundaries of the habitable zone in the universe. Traditionally, astronomers have defined a habitable world strictly by its orbital distance from a host star, searching for planets warm enough to maintain liquid water on their sunlit surfaces. But the biological engines operating beneath the Antarctic ice prove that solar radiation is entirely optional. If life can be sustained purely by the mechanical friction of a grinding ice shell and the slow decay of planetary bedrock, the dark void of space suddenly becomes radically fertile. And right here, this biological mechanism begins to connect to much larger, existential questions regarding the silence of the cosmos. When scientists debate the Fermi paradox, pondering why we have not detected any signals from advanced extraterrestrial civilizations, they often assume life is a surface phenomenon. But the lessons of the Antarctic subglacial lakes suggest a deeply humbling alternative. What if the default state of cosmic biology is not sprawling across a sunlit surface, but hiding in the pressurized dark? Across our own solar system, moons like Europa and Enceladus possess the exact same physical dynamics. A crushing outer ice shell, a deep liquid ocean, and a rocky core constantly pulverized by gravitational tidal forces. The hidden microbial ecosystems of Antarctica are the absolute proof of concept that these alien, ice-covered oceans have all the necessary chemical machinery to support enduring biospheres. It strongly suggests that when we finally find life beyond Earth, it will not be basking in the starlight, but slowly eating the ancient rocks buried in the dark, silent depths of a frozen world. When we conceptualize the discovery of microscopic life in extreme environments, human intuition often relies on the imagery of a liquid soup. We imagine solitary bacterial cells floating freely through the dark subglacial lakes, independently hunting for microscopic flakes of pulverized rock. But the biological reality operating beneath the Antarctic ice sheet completely upends this model. In a severely energy-deprived environment, floating freely is a thermodynamic death sentence. A solitary cell drifting in the water column is disconnected from its primary energy source, which is the mineral-rich bedrock. To survive the crushing darkness of the subglacial world, these organisms have completely abandoned the planktonic, free-floating lifestyle. Instead, they build cities. The fundamental architecture of deep subglacial life is the biofilm. Rather than floating, these microbial communities aggressively anchor themselves directly to the rock surfaces, binding together to form highly structured, multi-layered biological mats. To achieve this, the bacteria secrete a complex matrix of extracellular polymeric substances, essentially a robust biological glue composed of long-chain sugars, proteins, and ancient DNA. This matrix is not just a physical tether, it is a highly sophisticated closed-loop infrastructure. It shields the internal community from sudden shifts in hydrostatic pressure, neutralizes toxic heavy metals, and most importantly, it acts as a localized biochemical grid. Within this microscopic matrix, a phenomenon known as syntrophy takes place. Because the energy margins of eating raw rock are so incredibly thin, no single species of bacteria possesses the complete metabolic machinery required to process the minerals efficiently. Therefore, they divide the labor. One layer of the biofilm might specialize in oxidizing iron, producing a specific chemical waste product. The adjacent layer of entirely different bacteria has evolved to use that exact waste product as its primary fuel, stripping the remaining electrons before passing the secondary waste down to a third layer. This is not merely a collection of organisms, it is a single, highly integrated metabolic engine. They have engineered a system where the concept of biological waste completely ceases to exist. Every electron is fiercely traded and fully consumed before it leaves the biological grid. But this organizational mechanism leads to a much deeper, profound realization regarding how we search for life beyond our planet. The biofilm model of Antarctica fundamentally dictates the engineering parameters for the entire field of astrobiology. Currently, space agencies are designing orbital probes to study the icy moons of the outer solar system, such as Jupiter's Europa and Saturn's Enceladus. We know these moons harbour deep, dark, pressurized oceans beneath kilometers of solid ice. However, the Antarctic data suggests a severe limitation to our current observational models. If alien life exists in those extraterrestrial oceans, the vast majority of the biomass will not be swimming freely in the water. It will be fiercely locked away in dense sessile biofilms, gripping the hydrothermal vents and rocky seafloors, hundreds of kilometers below the icy surface. This presents a massive technical blind spot. When a probe like the Cassini spacecraft flies through the geyser plumes erupting from the surface of Enceladus, tasting the ejected water for signs of life, it is effectively sampling the most barren part of the ecosystem. The water column might only contain a microscopic fraction of dead or detached cellular debris, while the true, thriving biological metropolis remains anchored to the core, entirely invisible to our instruments. To truly confirm the existence of alien life, we cannot simply skim the surface water. We will eventually have to design autonomous submersibles capable of melting through miles of alien ice to physically scrape the bedrock of another world. And right here, this biological architecture begins to connect to a much larger question about the ultimate fate of civilizations. When astrophysicists debate the Fermi paradox, the glaring contradiction between the high probability of extraterrestrial life and the absolute silence of the cosmos, they often search for a great filter. This filter is a hypothetical evolutionary barrier that prevents simple life from evolving into a spacefaring, communicative civilization. The biofilm ecosystems of Antarctica offer a deeply humbling and entirely physical solution to this cosmic silence. Planetary scientists now believe that ice-capped ocean worlds are likely the most common type of habitable environment in the universe, vastly outnumbering rocky, sunlit planets like Earth. If the fundamental architecture of life in these dark oceans defaults to deep, benthic biofilms, the evolutionary trajectory of the cosmos shifts dramatically. A biological network trapped beneath 20 kilometers of solid ice, sustained purely by slow chemical syntrophy, possesses absolutely no evolutionary incentive to develop complex nervous systems, let alone conceptualize astronomy. Even if multicellular organisms were to evolve in that dark abyss, they would be permanently blind to the universe. They would never see a star. They would never discover combustion, because fire is impossible in a submerged environment. Without fire, there is no metallurgy. Without metallurgy, there are no radio telescopes. If this physical model holds true, it suggests that the universe is not sterile at all. It might be teeming with dense, ancient, and highly successful biological networks. But this life is universally sealed in sensory deprivation chambers of solid ice, forever isolated from the broader cosmos by a flawless thermodynamic barrier. The haunting implication of the Antarctic subglacial networks is that biology might be incredibly common, but the physical environment required to forge a communicative civilization might be one of the rarest anomalies in the physical universe. When geologists drill deep into the bedrock of the transantarctic mountains, they do not just find sterile stone. They extract core samples packed with the fossilized remains of giant ferns, ancient tree trunks, and the bones of massive terrestrial dinosaurs. These biological artifacts prove that the blinding white desert we see today is a relatively recent geological phenomenon. For the vast majority of its history, Antarctica was not a frozen wasteland. It was the lush, temperate, and vibrant heart of the ancient supercontinent known as Gondwana. To understand how a thriving biological paradise transformed into a cryogenic tomb, we must look at the slow, violent mechanics of plate tectonics and the catastrophic power of planetary ocean currents. Over 100 million years ago, immense thermal plumes rising from the deep mantle of the Earth began to tear Gondwana apart. The tectonic plates carrying modern-day Africa, India, and eventually Australia slowly sheared away from the central Antarctic landmass, drifting northward toward the equator. However, for tens of millions of years, Antarctica remained connected to the southern tip of South America by a solid land bridge. As long as this terrestrial tether held, the global climate remained highly regulated. The configuration of the oceans allowed warm tropical currents from the equator to travel freely down toward the southern pole, bathing the Antarctic coastline in thermal energy and keeping the continent entirely free of permanent ice. But this warm global greenhouse was fundamentally fragile, completely dependent on a single geological bottleneck. Approximately 34 million years ago, the relentless tectonic engine finally snapped the last connection. South America was forcefully pulled away from the Antarctic Peninsula, violently tearing open a deep water channel known today as the Drake Passage. At roughly the same time, the ocean gap between Antarctica and Australia, known as the Tasman Gateway, widened into a massive, deep water basin. The seventh continent was suddenly physically severed from the rest of the terrestrial world. The physical severing of these land bridges triggered an oceanographic cascade that permanently altered the climate of the Earth. Without any continental landmasses blocking the path, the furious westerly winds that dominate the southern hemisphere began to drive the ocean water in a continuous, uninterrupted circle around the globe. This birthed the Antarctic circumpolar current, driven by the rotational energy of the planet and completely free of any terrestrial friction. This current rapidly amplified into the most powerful fluid dynamic force on Earth. Today, it moves over 150 million cubic meters of water per second, dwarfing the combined flow of every single freshwater river on the planet. But the true devastating power of the Antarctic circumpolar current is not its immense speed or volume. It is its function as an impenetrable thermodynamic wall. Before the current formed, tropical heat easily flowed south. But once the circular vortex was established, it created a massive high-velocity barrier. When warm equatorial waters move southward today, they violently collide with this massive wall of spinning cold water and are immediately deflected back toward the north. The current effectively sealed Antarctica inside a massive thermal quarantine, completely cut off from the planetary heat distribution network. The internal temperature of the isolated continent began to freefall. This abrupt thermal isolation triggered one of the most violent climate shifts in planetary history, a period known as the Eocene-Oligocene transition. As the temperatures dropped, winter snowfall in the high continental interior finally survived the summer melt. This initiated a catastrophic physical feedback loop known as the albedo effect. Because bright white snow reflects incoming solar radiation back into space much more efficiently than dark rock or green vegetation, the growing snowfields actively cooled the air above them. The colder it got, the more snow accumulated, and the more solar energy was rejected. Within a geological blink of an eye, the lush forests were annihilated, crushed beneath a rapidly advancing dome of solid ice. Antarctica froze itself alive. At a planetary scale, the meaning of this tectonic shift changes completely. The freezing of Antarctica forces us to radically re-evaluate our entire mathematical approach to astrobiology. When astronomers search the galaxy for habitable exoplanets, they primarily focus on the Goldilocks zone, calculating the precise orbital distance required for a planet to receive enough stellar radiation to maintain liquid water. But the violent climate history of the Earth proves that stellar radiation is entirely secondary to internal tectonic geometry. If a slight shift in the arrangement of continental plates can spontaneously generate an ocean current powerful enough to plunge an entire hemisphere into a deep freeze, then the habitability of a rocky world is incredibly precarious. It suggests that finding a planet at the perfect distance from its star guarantees absolutely nothing. If the alien world possesses the wrong continental configuration, its oceans might inherently work against the survival of a complex biosphere, blocking heat transfer and initiating runaway glacial events. And right here, this geological mechanism connects deeply with the looming shadow of the Fermi paradox. We often imagine that the great filter, the hypothetical barrier that prevents simple life from evolving into advanced civilizations, takes the form of asteroid impacts, gamma ray bursts, or nuclear self-destruction. But the formation of the Antarctic circumpolar current presents a much quieter, slower, and far more common planetary executioner. It is a tectonic great filter. A thriving, highly evolved ecosystem can be completely eradicated simply because the ground beneath it drifts a few degrees in the wrong direction, opening a fatal ocean gateway. The dead, frozen forests of Antarctica are a permanent reminder that on any active world, the climate is never truly stable. It is merely waiting for the tectonic locks to break. While the East Antarctic craton remains a monolithic anchor of geological stability, the western sector of the continent presents a terrifyingly different reality. If the east is a fortress, the west is a sieve. Recent seismic tomography has unveiled that West Antarctica is situated atop an extensive, highly active volcanic rift system known as the West Antarctic Rift. This geological feature is a massive spreading tear in the crust, where the Earth's lithosphere is actively pulling apart, thinning the mantle, and creating a highway for deep crustal heat to rise directly toward the surface. Unlike the ancient cold roots of the East, the West Antarctic crust is hot, thin, and dangerously compliant. This rift system is not a dead, dormant curiosity of the distant past. It is currently pulsing with activity. Beneath the miles of ice, a massive chain of volcanic centers and geothermal hotspots continuously leaches energy into the base of the ice sheet. We are not talking about erupting volcanoes in the traditional sense, spewing fire into the sky. We are discussing broad, diffuse thermal flux, the silent, steady pumping of heat from the deep earth, warming the water trapped between the ice and the rock. This geothermal infusion fundamentally alters the physics of the ice sheet. It turns the base of the glacier into a slushy, lubricated transition zone, effectively melting the ice from below at a rate that is completely invisible to satellite sensors monitoring surface temperatures. This geothermal heating provides a primary driver for the accelerated movement of the West Antarctic ice streams. By warming the basal water, the rift system acts as a persistent thermal lubricant, drastically reducing the friction that holds the ice in place against the underlying bedrock. If the rift system were to suddenly flare in intensity, or if deeper mantle plumes were to shift positions, the entire mechanical equilibrium of the West Antarctic ice sheet could shift. The ice is not just being melted by the warming atmosphere above, it is being toasted from below by the very planet it rests upon. But the problem does not stop there. The West Antarctic Rift reveals a crucial vulnerability in our current climate models. Scientists traditionally rely on surface weather data to predict how quickly the Antarctic ice will collapse. However, the presence of this active, hidden volcanic rift demonstrates that the ice sheet is subject to variables that exist completely independent of the atmospheric climate. The heat flux from the rift can change regardless of global warming. It is a geological variable, not a meteorological one. This introduces a major uncertainty in our ability to predict future sea level rise. If the geothermal flux beneath the West Antarctic ice increases due to tectonic shifts, the glaciers will accelerate their discharge into the ocean, regardless of how successful humanity is in reducing carbon emissions. we are forced to model a system that is influenced by two entirely different clocks: the fast, volatile tick of the atmosphere and the slow, heavy, deep crustal thrum of the mantle. At a planetary scale, the significance of this rift changes completely. This interaction between thin, rifting crust and overlying ice sheets is a fundamental mechanism that governs the evolution of planetary surfaces throughout the cosmos. When planetary geologists study the volcanic activity on Venus, or the long, expansive, tectonic trenches on Mars, they are examining the same process of crustal thinning and heat transport. If those worlds possessed significant polar ice caps, they would be subject to the exact same basal melting dynamics. The West Antarctic Rift teaches us that the structural integrity of an ice sheet is not just a function of the climate, it is a function of the underlying geophysics. And right here, this geological mechanism connects deeply with our broader understanding of habitable planetary development. For a world to be truly habitable, it must maintain a delicate balance between internal heat and surface stability. Too much internal heat, and the crust becomes a volcanic nightmare, unable to retain a stable atmosphere or water. Too little internal heat, and the planet goes geologically dead, lacking the tectonic recycling necessary to regulate its climate over deep time. West Antarctica is a perfect example of a world currently on the edge of this transition. It shows us that a planet can be locally unstable, with a highly active thinning crust, while maintaining a vast frozen exterior. The haunting implication of the West Antarctic Rift is that the stability of a civilization's home planet is entirely dependent on the structural longevity of its lithosphere. If a major tectonic rift were to open beneath a critical ice sheet of an alien civilization, it could cause a global, non-climatic cataclysm, destroying coastal infrastructure and destabilizing their global climate without any warning from the atmosphere. It reminds us that our civilization is not merely an inhabitant of the surface. We are passengers on a living, breathing, and occasionally tearing geological machine. Understanding the hidden heat of the West Antarctic Rift is not just about measuring the future of our sea levels. It is about recognizing that the very foundation of our planetary home is actively and permanently in flux. While the bedrock hidden beneath the ice tells the violent story of tectonic movement, the ice itself is a library of the planetary atmosphere. As snow falls across the vast, desolate Antarctic plateau, it does not simply pile up. Over thousands of years, the accumulation of new layers exerts a crushing pressure on the snow buried beneath. This pressure forces the individual flakes to recrystallize, squeezing out the trapped air and transforming the soft, white powder into dense, transparent, glacial ice. Crucially, during this transition, tiny bubbles of the local atmosphere are pinched off and permanently sealed within the crystalline structure. These bubbles are not mere imprints. They are literal time capsules containing pressurized, pristine samples of the Earth's atmosphere as it existed hundreds of thousands of years ago. To extract these prehistoric records, scientists utilize advanced rotary drills, pulling out long, cylindrical ice cores from kilometers deep within the continental interior. By analyzing these cores, we can directly measure the concentration of ancient greenhouse gases, such as carbon dioxide and methane, at specific points in deep time. This is not a reconstruction based on secondary proxies. It is an analytical measurement of an atmosphere that has been physically preserved in a cryogenic vault. It provides a direct, empirically validated history of the Earth's chemical composition over the past 800,000 years. However, interpreting the history of the Earth's temperature is more complex than simply measuring gas bubbles. For this, scientists utilize the isotope geochemistry of the ice itself. Oxygen molecules in the water consist of different isotopes, variants of the same element that differ slightly in their atomic mass. These are primarily the lighter oxygen-16 and the heavier oxygen-18. The ratio of these two isotopes in the ice is directly dependent on the global temperature at the time the precipitation originally formed. The physical mechanism is simple but robust. Heavier oxygen, 18 molecules, require more energy to evaporate from the ocean's surface and tend to condense out of the air more rapidly as a storm system moves from the warm equator toward the freezing poles. Therefore, snow that falls during a colder climate period is significantly more depleted in oxygen-18 than snow that falls during a warmer interval. By measuring these minute fluctuations in the isotopic ratio throughout the length of an ice core, scientists can construct a high-fidelity graph of the planetary temperature across the last million years. It is an atomic thermometer that records the pulses of the Earth with incredible precision. But the problem does not stop there. The ice core record is not a perfectly linear tape. As the ice flows and deforms under its own weight, the deeper layers are stretched and compressed, eventually becoming chaotic and unreadable as they approach the bedrock. This mechanical degradation imposes an absolute limit on our ability to look back into the past. Currently, the most ambitious projects are attempting to identify regions of the continent where the ice is so thick and the flow so slow that the oldest, deepest layers remain undisturbed. They are racing to extract a core representing 1.5 million years of history. This specific milestone is not just a curiosity, it is a critical scientific threshold. 1.5 million years ago, the Earth experienced a major transition in the frequency of its glacial cycles, shifting from a 40,000-year cycle to a 100,000-year cycle. Scientists hypothesize that a change in the concentration of atmospheric carbon dioxide triggered this transition, but we lack the physical data to confirm this. Finding that 1.5 million-year-old ice would be the smoking gun to understanding how the climate system shifts between different modes of planetary stability. At a planetary scale, the meaning of these ice cores shifts completely. They provide the fundamental baseline for everything we understand about the human impact on the modern climate. Without the ice core record, the rapid, unprecedented rise in atmospheric greenhouse gases since the Industrial Revolution would exist only as an abstract theory. Because of the ice cores, we can state with statistical certainty that the current carbon levels are higher than at any point in the last million years, and the rate of change is effectively vertical compared to the natural oscillations of the deep past. And right here, this methodology connects directly to the broader field of astrobiology and the search for life elsewhere in the universe. If we were to send a probe to a world like Europa, our primary objective would be to perform the exact same analysis. We would melt the surface ice, extract the trapped bubbles of gas, and measure the isotope ratios. If the atmosphere of an alien world showed a massive, non-equilibrium fluctuation in methane or oxygen, it would be the most profound biomarker we could possibly hope for. The techniques we perfected in the frozen interior of Antarctica are the foundational tools of modern planetary exploration. We are using the history of our own world to define the language we will use to listen for the voices of others. The ice core record acts as a planetary metronome, ticking in time with the subtle mathematical geometry of the Earth's orbit around the Sun. For hundreds of thousands of years, the climate of our world has been dictated by the Milankovitch cycles, a series of periodic fluctuations in the Earth's eccentricity, axial tilt, and precession. These subtle variations change the amount and the distribution of solar energy reaching our atmosphere. When the orbit is most eccentric and the tilt is most pronounced, the planet slides into a warm interglacial period. When the orbit circularizes and the tilt diminishes, the Earth falls into a deep, long-duration ice age. These orbital mechanics are the primary drivers that have governed the rhythm of our climate for millions of years. Within the Antarctic ice, we can observe the exact correlation between these orbital changes and the natural concentration of atmospheric greenhouse gases. During the glacial cycles of the last 800,000 years, carbon dioxide levels naturally oscillated between roughly 180 parts per million during the coldest depths of the ice ages and 280 parts per million during the warmest interglacial peaks. This is the natural heartbeat of the planet, a slow, regulated respiration of the Earth's climate system, driven by the physics of gravity and orbital motion. But the data extracted from the most recent ice layers reveals an anomaly that is physically unprecedented. Since the beginning of the Industrial Revolution, the concentration of atmospheric carbon dioxide has soared to over 420 parts per million, and methane levels have more than doubled their highest natural peaks. We are no longer observing a climate driven by orbital mechanics. We have introduced an entirely new anthropogenic variable into the equation. The rate of increase is not gradual, it is vertical. We have fundamentally decoupled the atmospheric composition from the historical rhythm of the orbital cycles. The implications of this shift are profound when considering the potential for positive feedback loops. As the planet warms due to this human-induced spike in greenhouse gases, the massive stores of carbon currently locked in the permafrost of the northern hemisphere and the subglacial sediments of the southern hemisphere begin to destabilize. Methane, a greenhouse gas significantly more potent than carbon dioxide in the short term, is stored in massive quantities as clathrates, methane hydrates trapped in the deep sea floor and frozen soil. If the warming trend crosses a critical threshold, these stores could be released into the atmosphere in a rapid, self-reinforcing eruption of greenhouse gases. This presents a terrifying paradox for the future of climate modeling. We are currently pushing the planet into a state of thermal energy that has not been seen in millions of years, far exceeding the natural range established by the Milankovitch cycles. The ice core record serves as a warning because it defines the boundaries of the system that we are currently overstepping. We have no historical data from the ice cores that shows the Earth adapting to such a rapid, sustained shift in atmospheric chemistry. We are conducting a high-stakes, planetary-scale experiment without a control group. At a planetary scale, the significance of this shift changes completely when viewed through the lens of astrobiology and the potential for technological civilization. When SETI researchers and astrobiologists look at the potential for life on other planets, they are searching for signs of atmospheric disequilibrium, a state where the chemical makeup of an atmosphere cannot be explained by non-biological, geological, or volcanic processes alone. We are now creating a planetary atmosphere that is fundamentally out of equilibrium, not just due to biology, but due to rapid, intentional, and massive technological interference. If an advanced alien civilization were observing our planet from a distance of many light years, they would not see a natural, orbiting body governed by the slow rhythm of its star. They would see a chemical signature that screams of an industrial, technological, and potentially destabilizing presence. And right here, this mechanism connects deeply with our broader understanding of the Great Filter. The transition from a climate governed by natural orbital cycles to a climate governed by anthropogenic emissions may be a standard milestone for any civilization that discovers the power of burning fossilized carbon. It represents a potential developmental bottleneck, a moment where the planet's natural self-regulating systems are overwhelmed by the byproduct of technological progress. If other civilizations in the galaxy face the same orbital and chemical constraints, then the ability to survive this transition without permanently destabilizing their homeworld may be the ultimate hurdle in the evolution of any spacefaring culture. The ice cores of Antarctica are not just a record of our past. They are a direct, quantifiable measurement of how quickly a civilization can alter the fundamental physics of its own planetary habitability. We are, quite literally, forcing our world to evolve faster than its own geological history can keep up with. Beneath the surface chaos of Antarctica lies a physical environment of such absolute unnatural purity that it has become the most coveted laboratory for high-energy particle physics in the world. As the ice accumulates over hundreds of thousands of years, the intense pressure forces out every microscopic bubble of air, every speck of dust, and every trace of chemical impurity. The result is a medium of extreme optical clarity and structural uniformity. This deep, ancient ice is not merely frozen water. It is a gargantuan, transparent detector, and it is currently being used to trap the most elusive entities in the universe: neutrinos. Neutrinos are fundamental particles produced in the most violent events in the cosmos: supernova explosions, black hole mergers, and the hearts of active galactic nuclei. They are often called ghost particles because they possess almost no mass and carry no electrical charge. They stream through the Earth, through the Sun, and through the human body by the trillions every second, rarely interacting with matter at all. To catch them, you cannot use a conventional telescope or a silicon chip. You need a target so massive and so perfectly clear that even a ghost particle has a non-zero probability of colliding with an atom and triggering a detectable cascade. The IceCube Neutrino Observatory, located at the South Pole, exploits the unique physics of the Antarctic ice sheet to solve this problem. Scientists have drilled thousands of meters into the deep, pristine ice and deployed an array of sensitive digital optical modules. The principle is elegant in its simplicity. When a high-energy neutrino from a distant galaxy manages to strike an atom within the ice, it generates a secondary particle that travels faster than the speed of light within that medium, creating a faint, localized flash of blue light known as Cherenkov radiation. Because the deep Antarctic ice is so incredibly transparent and free of scattering impurities, these faint photons can travel hundreds of meters without being blocked or absorbed. The optical modules detect these flashes, and by mapping the timing and geometry of the light, physicists can reconstruct the trajectory of the neutrino back to its point of origin in the deep cosmos. We are essentially using an entire continent as a massive, subterranean eye to observe the high-energy processes of the universe. But the utility of this medium goes beyond just neutrino detection. The Antarctic ice sheet serves as a natural filter of both time and space. Because the ice is so stable and free of radioactivity, it provides a background of absolute silence. In physics, the biggest challenge is signal-to-noise ratio. The more noise in your detector, the harder it is to see the signal of a rare event. The Antarctic ice offers a near-zero radioactive background, allowing us to perceive the faint, high-energy echoes of the universe that would be completely swamped by the natural radioactivity of the Earth's crust in any other location. However, the use of this medium is limited by the very geological processes that create it. The ice is not perfectly static, it flows. Over tens of thousands of years, the internal deformation of the glacier can shift the orientation of the detector array, requiring constant, highly precise calibration. Furthermore, as the climate warms, the increase in meltwater at the surface can introduce impurities that slowly percolate downward, threatening to contaminate the optical clarity of the deep detectors over multi-decadal timescales. We are operating in a race against the very environment we are utilizing. At a planetary scale, this reveals a profound truth about how our civilization interacts with our home world. We are transitioning from using the Earth as a simple platform for living to using the Earth as a specialized piece of scientific apparatus. The Antarctic ice sheet has been repurposed from a geophysical feature into a fundamental component of global astronomical infrastructure. And right here, this concept bridge links directly to the search for intelligence in the universe. If any other advanced civilization were to develop a deep space research program, they would inevitably seek out the most extreme, pristine, and stable physical environments available on their own planet to act as natural detectors. If we look at the cosmic silence and wonder where the other civilizations are, perhaps we are looking at the wrong wavelengths. They might be hiding in plain sight, having converted the deep interiors of their own icy moons or polar regions into massive, planet-scale sensors. The pristine ice of Antarctica is not just a place where we study the universe. It is a prototype of how a mature, technological civilization utilizes the unique physical properties of its own world to peer into the heart of the cosmos. We are not just observing the distant stars, we are learning how to transform the cold, frozen foundations of our own home into an instrument of infinite reach. While Antarctica acts as a detector for the ethereal ghost particles of the universe, it simultaneously functions as a massive, naturally occurring collector for the physical debris of the solar system. Millions of meteorites have fallen onto the continent over the last several million years. In most terrestrial environments, these visitors from space are quickly lost. They are buried by soil, weathered away by rain, or consumed by the rampant growth of vegetation. But in Antarctica, the environment is fundamentally different. When a meteorite lands on the high interior ice sheet, it is immediately cryogenically preserved. It does not rust, it does not rot, and it does not disappear. It becomes a frozen artifact, locked inside the slow-moving conveyor belt of the glacier. The mechanism that transforms this frozen debris into a searchable collection is a complex interaction between ice flow and topographic barriers. As the massive glaciers of the interior slowly creep toward the coast, they eventually encounter the colossal obstruction of the Transantarctic Mountains. The mountains act as a giant, physical dam. The ice is forced to rise over the peaks, but as it encounters the cold, dry winds descending from the high plateau, the surface ice begins to undergo a process known as sublimation. This is a direct phase transition where solid ice turns into water vapor without ever passing through the liquid phase. The ice effectively evaporates into the thin, dry air, leaving behind everything that was embedded within it. Over hundreds of thousands of years, this process acts as a geological filter. The glacier continuously delivers meteorites to these mountain barriers. The ice thins through sublimation, and the meteorites are left stranded on the surface in concentrated zones. We call these meteorite stranding surfaces. For planetary scientists, these patches of dark, pitted stones sitting atop the blue ice are the most valuable real estate on the planet. They are not random collections. They are curated archives of the solar system's formative years, perfectly preserved and delivered to the surface, by the slow mechanical motion of the continent. But the importance of these samples extends far beyond mere mineral collection. Because they are preserved in a cold, sterile environment, they remain remarkably free from terrestrial biological contamination. When scientists analyze these stones, they are touching material that has not been altered by the chemical or biological evolution of the Earth. Some of these meteorites are primitive chondrites, the literal building blocks of the solar system, holding water and organic molecules that date back to the birth of the Sun 4.6 billion years ago. Others are igneous rocks blasted off the surface of Mars by ancient asteroid impacts, providing us with direct geological samples of our planetary neighbor without the astronomical cost of a return mission. However, this natural concentration mechanism comes with a strict chronological limit. The meteorites that are successfully recovered are only those that have been captured by the ice flow within the last few million years. Meteorites that fell earlier were carried into the deep ocean or were crushed beyond recognition by the immense pressures at the base of the ice sheet. We are effectively observing a window of space debris. We have no way of knowing what rare, exotic materials from even older cosmic events might have fallen to Earth in the deep past, only to be permanently recycled into the mantle by the shifting plates of the crust. At a planetary scale, the existence of these meteorite fields changes our perception of the Earth's role in the cosmic environment. Our planet is not an isolated, safe island. It is an active participant in a violent, high-speed collision course with the rest of the solar system. The sheer density of meteorites found in these Antarctic stranding zones suggests that the Earth is constantly being bombarded by a massive, continuous influx of extraterrestrial material. And right here, this physical mechanism bridges directly into the most significant debates in astrobiology and the potential for life. The most famous specimen ever recovered from these Antarctic ice fields is a rock named ALH 84001, a meteorite identified as having originated from Mars. In the late 20th century, researchers claimed to find microscopic structures within this stone that resembled fossilized bacteria. While the scientific consensus on those specific structures remains heavily debated and skeptical, the broader implication is undeniable. The exchange of planetary material is a constant physical reality. If a major impact event can blast chunks of a habitable, rocky world across the vacuum of space to land on another planet, then life itself could be a planetary traveler. This concept, known as panspermia, suggests that life might not necessarily originate on the planet where it is discovered. It could be transferred between worlds via the very meteorites that we are currently harvesting from the Antarctic ice. The Antarctic stranding zones are therefore not just a collection of rocks. They are the physical evidence of a massive interplanetary transit system. They remind us that the great filter, that hypothetical barrier preventing the spread of life, might not be a biological impossibility, but a physical one. We are learning that the universe is constantly sharing its material, seeding the chemistry of one world with the rocks of another. Antarctica is the terminal for this cosmic freight, allowing us to hold the history of the solar system in our hands, provided we have the vision to read the stories written in the stones. At the edge of the West Antarctic continent, where the vast, miles-thick ice sheet meets the Southern Ocean, lies the most significant physical bottleneck in the modern climate system, the Thwaites Glacier. Often referred to by the media as the Doomsday Glacier, this moniker obscures the complex, mechanical reality of what is truly happening. Thwaites is not an inherently unstable monolith waiting to shatter. It is a structural keystone. It acts as a massive physical dam, holding back the immense gravitational pressure of the inland ice sheets. To understand why this glacier is the focus of intense scientific anxiety, we must move beyond the imagery of melting and look at the fluid mechanics of the grounding line. The grounding line is the specific geographical and physical boundary where the ice sheet lifts off the bedrock and begins to float as an ice shelf on the ocean's surface. This transition zone is the most critical point of vulnerability in the entire West Antarctic system. The bedrock beneath the Thwaites Glacier is configured in a deep retrograde slope. It tilts downward as you move inland toward the center of the continent. This is a classic geological trap. Because the ice rests on a floor that deepens inland, the thickness of the ice at the grounding line increases the further it retreats. A thicker ice front is inherently more unstable. It experiences greater mechanical stress and moves faster, which forces the grounding line to retreat even further into deeper water. This is the marine ice sheet instability mechanism. It is a runaway, self-sustaining feedback loop. Once the grounding line is forced back beyond a certain topographical threshold, the physics of the system mandate that the retreat must continue until the ice reaches higher ground. There is no structural break to stop the process. And right here, the ocean dynamics intervene to accelerate the catastrophe. Deep, relatively warm circumpolar water is constantly being pushed onto the continental shelf by complex wind patterns. This warm ocean water flows underneath the floating ice shelf, reaching the grounding line and melting it from below. This subshelf melting thins the ice, reducing its structural buttressing effect on the inland glacier. As the ice shelf loses its integrity, the glacier behind it flows faster, delivering more ice to the ocean, which in turn causes the grounding line to retreat further inland into the deep retrograde basin. We are observing a structural collapse driven by the relentless, invisible intrusion of the deep ocean into the foundation of the continent. But the problem does not stop there. There is a secondary, even more theoretical process known as marine ice cliff instability. If the thinning process is rapid enough, the ice front of the glacier could eventually exceed its own structural limit, causing the massive, towering ice cliffs to shatter under their own weight. This would expose an even taller face of ice to the ocean, triggering a cascade of failures that could lead to the rapid, multi-decade disintegration of the entire West Antarctic ice sheet. While this specific mechanism remains a subject of intense scientific debate and modeling, as we have never observed such a collapse at this scale, the mathematical models consistently point to the structural limits of ice. At a planetary scale, the importance of this mechanic is not merely about the loss of coastal cities. It is about the redistribution of the planetary mass. The West Antarctic ice sheet contains enough water to raise global sea levels by several meters. Such a massive injection of fresh water into the Southern Ocean would fundamentally alter the salinity and density of the surface water, which is the primary driver for global oceanic circulation. If the Thwaites Glacier reaches its threshold of instability, it could disrupt the global conveyor belt of heat distribution, triggering a chain reaction of climatic shifts that extend far beyond the coastlines of the planet. And right here, this geological mechanic bridges into the most existential questions regarding the nature of civilization. The existence of a planetary-scale, self-accelerating collapse mechanism implies that even in a stable climate, the structural geometry of our world is subject to catastrophic, non-linear events. Our modern civilization, with its high-density coastal population centers, is essentially built on a foundation that has been geographically static for 10,000 years. We are currently testing the limits of this stability. If we consider the Fermi paradox, the Great Filter might not be an external force like an asteroid, but the inherent vulnerability of a high-tech civilization trying to maintain a permanent global footprint on a geologically active and topographically sensitive planet. We are witnessing the mechanics of planetary change in real time. The Thwaites Glacier is not just a block of melting ice. It is a live physical demonstration of how a structural transition at the grounding line of a continent can rewrite the map of the world. It reminds us that our civilization's long-term survival is predicated on our ability to map, understand, and anticipate these invisible, threshold-driven mechanical failures before they become irreversible. The ice does not care about our geography. It only obeys the uncompromising physics of gravity, fluid pressure, and bedrock slope. The collapse of an ice sheet is not a simple surface-level melting event. It is a complex, three-dimensional mechanical failure. At the grounding line, the point where the ice rests on the continental shelf, the ocean exerts a relentless, unseen pressure. Recent oceanographic research, deploying autonomous submersibles beneath the thick ice shelves, has revealed that deep, relatively warm circumpolar water is constantly being forced into the sub-ice cavities. This water is not warm enough to boil or rapidly vaporize the ice, but it is precisely warm enough to significantly accelerate the rate of basal melting. As this deep water melts the ice from below, the grounding line is forced to retreat. This retreating grounding line initiates a catastrophic physical transition. As the glacier detaches from its bedrock anchorage, it loses the massive frictional resistance that previously held its movement in check. It begins to slide more rapidly toward the ocean. This increased velocity thins the glacier, which in turn causes the floating ice shelf to stretch and develop deep structural fractures. These fractures provide new, easier pathways for warm ocean water to penetrate even further inland, creating a self-reinforcing, positive feedback loop that accelerates the total structural decay of the marine-based ice sheet. But the physical consequence of this massive loss of ice weight extends far beyond the ocean. We must consider the geophysics of the solid Earth itself. For hundreds of thousands of years, the immense crushing mass of the Antarctic ice sheet has physically depressed the continental crust into the Earth's mantle, a process known as isostatic depression. When this massive load is removed, when trillions of tons of ice are lost to the ocean, the underlying lithosphere is no longer held down by the weight. It begins to undergo a process of isostatic rebound, a slow, viscous rise of the continental crust as it attempts to reach a new state of gravitational equilibrium. This rebound is not a local event. It is a profound alteration of the planet's surface geometry. As the Antarctic bedrock rises, it physically pushes against the bottom of the remaining ice sheet. In some models, this could potentially slow the flow of the glaciers by creating new, uplifted ridges of bedrock that act as physical dams. However, this same movement also generates intense, localized seismic stress within the continental crust. We are currently observing a global redistribution of mass that is subtly altering the Earth's rotation, shifting the position of the geographic poles, and fundamentally changing the distribution of gravity across the entire globe. This leads to a complex, non-intuitive secondary effect on sea level rise. As the massive gravity of the Antarctic ice sheet decreases, the gravitational pull that historically kept a significant volume of ocean water clustered around the South Pole also weakens. Consequently, as the ice melts, the oceans do not simply rise uniformly like water in a bathtub. Instead, they recede near Antarctica and surge disproportionately toward the northern hemisphere. The very geography of our coastline is being rewritten by the shifting gravitational field of the planet. At a planetary scale, this interplay between marine erosion and crustal rebound is a fundamental mechanism of geological evolution. When we study the ancient sedimentary records of previous interglacial periods, we see evidence of these same massive, rapid shifts in coastal topography. It is a reminder that the boundary between land and ocean is not a static line. It is a fluid, dynamic equilibrium constantly renegotiated by the weight of the ice and the resilience of the crust. And right here, this physical mechanism bridges to the broader existential questions regarding the longevity of our civilization. Our global coastal infrastructure is currently calibrated to a planetary configuration that is arguably an anomaly, a fleeting period of relative stability in a much larger and far more violent geological history. The great filter in our planetary evolution may not be the climate itself, but our inability to adapt our high-density, static infrastructure to a planet that is structurally and gravitationally dynamic. If we are to survive as a spacefaring species, we must develop the scientific maturity to not only predict the weather, but to anticipate the slow, massive, and inevitable adjustments of the solid crust beneath our feet. We are attempting to build a permanent future on a foundation that is actively and permanently seeking a new balance in the wake of our planetary scale interference. The final piece of the Antarctic puzzle lies not in the ice itself, but in the massive, invisible conveyor belt of the global ocean. Antarctica is the primary engine of this system through the formation of Antarctic bottom water. This is the coldest, densest water on the planet, produced when sea ice freezes along the Antarctic coastline. As the ice forms, it rejects salt, creating a hypersaline, freezing brine that sinks rapidly down the continental shelf and spills into the deep ocean basins. This dense plume of water then creeps across the global seafloor, effectively acting as a massive, slow-moving pump that drives the thermohaline circulation, the mechanism that redistributes heat, nutrients, and dissolved oxygen to every corner of the world's oceans. But current observational data indicates that this planetary pump is slowing down. As the ice shelves and glaciers of Antarctica undergo accelerated melting, they are injecting massive volumes of fresh, low-density water into the Southern Ocean. This freshwater influx is diluting the brine, reducing its density, and hindering its ability to sink. We are effectively clogging the intake of the global ocean's engine. If the Antarctic bottom water stops sinking, the entire thermohaline circulation could weaken or stall. The implications for the planetary climate are severe, as this circulation is the primary mechanism for sequestering heat and carbon dioxide into the deep ocean. The debate in the scientific community currently focuses on the rate of this decay. Some models suggest that the shutdown of the deep ocean circulation could happen within a few decades, potentially causing massive shifts in regional climates and triggering a breakdown in the marine food webs that rely on the nutrient-rich deep water returning to the surface. However, our current predictive capabilities are facing a critical limitation. We are struggling to model these changes because we cannot accurately capture the turbulence at the micro scale of the brine sinking events. The issue is a paradox of computational power. Supercomputers are currently unable to simultaneously model the entire global climate system while resolving the small-scale, chaotic fluid dynamics where the freshwater and saltwater actually mix. We are forced to use simplified parameterizations. Essentially, we are making educated guesses about the small-scale physics and hoping they don't fundamentally change the large-scale outcomes. This is the critical limit of our modern forecasting. We have the data to see the trend, but we lack the raw processing power to simulate the structural threshold at which the system will inevitably shift into a new, potentially less stable state. At a planetary scale, this limitation in our computational capacity highlights a massive, looming vulnerability. We are attempting to manage the stability of our civilization on a planet whose climate dynamics are increasingly complex and non-linear, using predictive tools that are structurally unable to capture the most critical moments of transition. If we cannot model the point at which the global conveyor belt stalls, we cannot prepare for the cascading consequences of that stalling. From localized sea level spikes in the North Atlantic to the destabilization of global monsoons that support the agriculture of billions. And right here, this technological gap bridges to the deepest existential questions we face regarding the future of intelligence in the universe. If we look at the potential for advanced life elsewhere, we must consider that any civilization attempting to survive on its home planet will eventually face the exact same technical hurdle. They will possess enough data to know that their climate is shifting, but they will likely find that the sheer complexity of planetary scale fluid dynamics exceeds the computational limit of their early technological era. The gap between knowing the danger and having the predictive power to manage the danger may be a universal great filter. The Antarctic bottom water system is a perfect, isolated case study of this struggle. It reminds us that our civilization is currently in a race, not just a race against carbon emissions, but a race to expand our capacity to understand, model, and anticipate the behavior of the complex planetary systems that maintain our environment. We are currently trying to pilot a starship while only having a rudimentary map of the engine room. Our future depends on whether we can bridge this gap between observational awareness and predictive mastery, or whether we will simply drift toward a planetary transition that we were smart enough to see, but not wise enough to stop.